Welcome to chapter 13, which is about acids and bases. In this chapter we're going to first off have a look at two different theories or models of acids and bases. In the next video we're going to have a look at the Bronsted-Lowry theory, but we're going to start off with the Arrhenius theory, which is an earlier model, and we're going to see how the Arrhenius theory is able to explain the properties of acids and bases. So as I mentioned, the Arrhenius theory, it's an older definition of acids and bases. It's also a more simplistic understanding of what makes something an acid or what makes something a base. And during this video, a lot of what I say you will find familiar, because this is the type of information that we teach to lower school students, years 9 and year 10, about what makes something an acid or what makes something a base. According to the Arrhenius theory, acids are substances that contain H in their formula, and they dissolve in water to form H+ ions. So, a great example of an Arrhenius acid would be hydrochloric acid, HCl, because the substance contains H in its formula and it dissolves in water to form H+ ions as well as chloride ions. So according to Arrhenius theory, it is the H+ ion which is actually the acidic thing, and the chloride ion is not, the acidic part of the molecule. As for what makes a base, Arrhenius said that bases are substances that contain OH in their formula, and they dissolve in water to form OH- ions. So another great example of an Arrhenius base is sodium hydroxide. Sodium hydroxide contains OH in its formula, and when it dissolves in water, it forms sodium ions plus hydroxide ions. And according to the Arrhenius theory of acids and bases, it's actually the hydroxide part of the substance which makes it basic, not the sodium part. So we can use this theory to explain why a lot of common acids and bases are acidic or basic respectively. Things that the Arrhenius theory can explain. It can explain why many of the common acids we use are actually acidic in terms of producing H+ ions. And it can explain why many bases that we use are basic in terms of hydroxide ions. If you had to actually explain why a substance is acidic using Arrhenius theory in a test, then this would be a really great opportunity for you to use an ionization equation. For example, if you got asked in a test, explain why nitric acid is acidic, then you could do an equation showing what happens when nitric acid dissolves in water. So it'd be HNO3 reacting to form H+ aqueous plus NO3 - aqueous. If you had to do an equation explaining why phosphoric acid is acidic using Arrhenius theory, your equation would have the phosphoric acid, H3PO4. Then you would have a reversible arrow, remembering that phosphoric acid, like most acids, is a weak acid. So it will undergo a reversible reaction to produce 3H+ plus phosphate. The key thing in both of these equations is that if we're using Arrhenius theory, we need to be showing how these substances produce H+, which is the part of them that makes them acidic. Similarly, you might need to, in a test situation, explain why certain substances are basic using Arrhenius theory. For example, potassium hydroxide and in these situations you would do a dissociation equation. So potassium hydroxide is KOH, and when it dissolves in water it forms K plus ions and hydroxide ions. And therefore, because this substance produces OH minus when it dissolves in water, it is considered basic under Arrhenius theory. The other good thing about this theory is it's able to help us explain why acids and bases can neutralize each other. If you consider an acid to basically be H plus ions in a solution, and you consider a base to be hydroxide ions in a solution, and you're thinking about, well, what actually happens when you mix together an acid with a base? It would form water. Water is a neutral substance. Acid plus base makes neutral. This is why it's called a neutralization reaction. So all these things Arrhenius theory is very good at, and that's why we still teach Arrhenius theory today. However, at your level, there start to become a few problems with Arrhenius theory. A few things that Arrhenius theory cannot actually explain about acids and bases. The first of these things, ammonia is one of our examples of a weak base. Ammonia has a formula of NH3. Earlier on I said that according to Arrhenius theory, all bases have OH in their formula. Ammonia obviously doesn't have OH in its formula, so therefore we need to modify our theory to explain why a substance like ammonia, NH3, could possibly be basic. The second thing that Arrhenius theory cannot explain is that some substances can be acidic or basic without actually being dissolved in water. Acetic acid is a typical example of this because the pure substance CH3COOH without any water occurs in the liquid phase at room temperature. And that substance, the pure acetic acid, does act like an acid. The reason why Arrhenius theory cannot explain this is because earlier on Arrhenius theory said that you need to dissolve the substance in water to form H plus ions, but you don't need to dissolve acetic acid in water to form H plus ions. And there are no H plus ions in the pure substance either, because acetic acid needs water to ionize. So somehow these neutral molecules are able to act like an acid. The third thing that Arrhenius theory cannot explain is that some salts from neutralization reactions are actually acidic or basic instead of being neutral. So for example, if you mix together hydrochloric acid, which is a strong acid, and ammonia, which is a weak base, the salt which you make is actually slightly acidic instead of being neutral. And Arrhenius theory cannot explain that. The final thing is that, or a major problem, H plus ions are unstable in water. They don't stick around for very long. So even if your hydrochloric acid did ionize to form H plus, that H plus ion actually will react with water to form what is called a hydronium ion, H3O plus. And the equation for that is shown here at the bottom. What it means is that the idea of Arrhenius that you just have these H plus ions isn't actually correct anyway, because you'd have H3O plus ions, not H plus ions. In the next video we're going to have a look at Bronsted-Lowry theory, which is a newer model of acids and bases, with the key idea being that Bronsted-Lowry theory can explain some of these things that Arrhenius theory cannot.